Next, we're going to introduce properties of continuous time Fourier transform. The first property is called linearity. Given that we have two pairs of Fourier transform, then the linear combination in the time domain of these two original signals will correspond to the same linear combination of the spectra of the two original signals, or vice versa. Here is one example. For a unit step function, it can be decomposed into two parts. So one is the DC component, the other one is the sine signal. So if we know the spectra of these two signals, then the spectrum of the unit step function will be equal to the linear combination of these two signals spectra. The second property is called conjugate symmetry. So if we know this pair of Fourier transform, then the conjugate of the signal in the time domain corresponds to the conjugate and then flip in terms of the vertical axis in the frequency domain. Similar thing if you go the other way around. The conjugate in the frequency domain corresponds to the conjugate and flipping in terms of the vertical axis in the time domain. So that's called conjugate symmetry. What if we know that the original signal in the time domain is a real function? Then we know this spectrum will be equal to capital X of j omega. And based on this restriction, then we know the amplitude of the spectrum will be an even function, while the phase spectrum will be an odd function. If you break the complex frequency spectrum into the real part and the imaginary part, then the real part will be an even function, while the imaginary part will be an odd function. If we put more restriction on the original signal x of t, if it's real and even, then this equation will be valid, and we can reach this conclusion that the spectrum of the original signal, if it is real and even, the spectrum will be real and even as well. But if the original signal is real but odd, the spectrum will be an imaginary and odd function. The third property is called duality. If we know the original signal x of t in the time domain has Fourier transform capital X of j omega in the frequency domain, we can switch their position. If we switch their position, this spectrum in the time domain, then the original signal in the time domain will be moved to the frequency domain, but with some change. The independent variable should be flipped in terms of the vertical axis, and also there will be a scaling factor 2 times pi in front of it. Still remember that for delta function, its spectrum is a DC component. And for DC components, its spectrum actually is equal to 2 pi times delta omega. So if we move this one to the time domain, then the original signal in the time domain will move to the frequency domain, but with a scaling factor 2 pi. And because this is an even function, so when you do the flipping, it is the original, it is itself. We can take another pair of Fourier transform. If this is a rectangle signal in the time domain, then its spectrum is a sampling function in the frequency domain. But if we move this one into the time domain, then this will be moved to the frequency domain and then multiplied by 2 pi. Since it is an even function, so flipping has no effect on its shape. The next property is scaling. Again, if this one is given, then scaling in the time domain will cause the inverse scaling in the frequency domain, and they also have some effect on the amplitude spectrum. So if this is a rectangle signal in the time domain, this will be the sampling function in the frequency domain. And if you extend it in the time domain, then the spectrum will be squeezed. So it will be compressed. Also, the amplitude will be changed as well. So this is the correspondence, extending or compression in the time domain corresponding to compression or extending in the frequency domain. The next property is time shift. If we have this pair of Fourier transform and you shift the original signal in the time domain, then the phase spectrum going to be changed in the frequency domain. So the amplitude spectrum will not change, but the phase spectrum will be shifted. So time shift in the time domain corresponds to phase shift in the frequency domain. Here is one example how we can make use of it to make our calculation easier. So we're asking you to calculate the spectrum of this rectangle signal. Since we know that this signal actually is a shifted version of the standardized or symmetric rectangle signal, so it is actually a time shift. And we know for the standardized rectangle signal, the spectrum is a sampling function like that. Then using the time shift property, we can figure out the spectrum for this time shifted rectangle signal as this phase shift of the spectrum of the standardized rectangle signal. It's quite straightforward. The next property is called frequency shift. So based on the duality, you can predict what's going to happen if you move the spectrum in the frequency domain along the frequency axis. So there will be extra phase shift. So frequency shift in the frequency domain will cause phase shift in the time domain, or you can say it the other way around. Phase shift in time domain causes frequency shift in the frequency domain. And here is one example. So this is the rectangle signal times a cosine function, and we are interested in find out the spectrum of this product. We know that for a rectangle signal, the spectrum is a sampling function. And this multiplication can be changed as using Euler equation, two terms of xt with phase shift. And phase shift in the time domain corresponds to frequency, phase shift corresponds to frequency shift in the frequency domain. And that is the results or the frequency spectrum of this product function in here. So if we take a look at the graphic representation or the waveform of the xt in the time domain, here is the corresponding spectrum. And multiply by cosine function, or if you do the phase shift in the time domain, here will be the frequency shift in the frequency domain. Because we use the Euler equation to break this part into two parts. So the spectrum will have to shift towards the left and right by a certain amount of frequency, which is happen to be the frequency of the original cosine function, and the amplitude of the spectrum will be reduced by half. The next one is time convolution. Given that we have two pairs of Fourier transform, and if we do the convolution in the time domain, then in the frequency domain, the corresponding spectrum will be equal to the spectra in product. So that is one more correspondence between the time domain and the frequency domain. Convolution in time domain corresponds to multiplication in the frequency domain. Here is one example how we can make use of that property to simplify our calculation. We are interested in the Fourier transform of this triangle signal. And we know that triangle signal actually is a convolution of a rectangle signal by itself. So here is the mathematical representation. And we know that for a standard rectangle signal, the sampling function is the spectrum. Convolution in the time domain corresponds to multiplication in the frequency domain. So for this signal, the spectrum will be the product or the square of this spectrum, which is 4 times squared sampling function. The next property is called frequency convolution. Again, you learn the duality property, so you probably can predict what's going to happen if you convolute the 2 spectra in the frequency domain. Then probably you're going to have a multiplication in the time domain, but subject to a scaling factor 2 pi. So there's another time frequency correspondence. Multiplication in the time domain corresponds to convolution in the frequency domain. Here is one more example, show us how to use that property. So we know that the triangle signal now is in the frequency domain. This is a spectrum. And what is the original signal that has the spectrum like that? We already know that the rectangle signal convolutes with itself will reach a triangle signal. So in the frequency domain, this original triangle spectrum can be treated as 2 rectangle spectrum in convolution. We know that rectangle signal and sampling function, they are a pair of Fourier transform. Now we just need to switch their position. So due to the duality property, if we know that the rectangle signal is in the frequency domain, then the sampling function is supposed to be in the time domain, so that we can write out the Fourier transform like this. You just switch the position and then here times 2 pi. And based on this understanding, the convolution in the frequency domain equal to the time production, the multiplication in the time domain, we can reach the conclusion that for the convolution in here, that will be the time function. So using this pair of Fourier transform, we can reach out for the triangle spectrum, the original time signal actually is equal to 2 over pi times squared sampling function.